whole thing recorded again. All right. So last time we have a trouble of missing the earlier section of it because I accidentally forgot to hit the record. I'm sorry for it. Okay, but that shouldn't happen again. All right. Now today we're going to talk about shear, but before we start, I want to take the first few minutes to go over some basic stuff. Okay. So let me say it again. We're going to have midterm exam take home. Okay, we're going to have midterm exam take home. The other thing, for the take-home exam, we're going to have a specific time frame for you to finish the exam. And also, we'll have a longer exam, a little bit harder, maybe, but we are not expecting students to work in group, nor we're expecting students to text message each other, find solutions. And I will tell you this, we'll have a different version of the exam as well. And you have different numbers. So I don't expect you guys to have same answers. Okay. All right. And now considering the class, this is what I'm going to do. You can mute and unmute yourself if you have any question during the class. And if somehow your voice cannot get through, you can message me. I can see the window right now. Okay. But once I see your message, I will stop and address your question as soon as I can. Okay. All right, and last but not least, we will have our Thursday lecture this week, okay? We will have our Thursday lectures this week. And the main reason for that is because considering now we have less time in terms of lecturing, so I want to make it up as much as we can, okay? And I'll go by the original schedule, but this week we will have a Thursday lecture. So for those of you who friends does not know that, please send a message and let them know. Okay? The homework is due midnight on Thursday, okay? Midnight, 12 o'clock, midnight on Thursday, okay? So as usual. All right? So any other questions? Any other questions, burning issues?
Oh, Dr. Bob?
Yes.
I just make sure many of us have Zoom meetings for water resources after this class.
Right.
And last time you went kind of long, and I ended up having to cut off the end of your lecture because I had to get on over to that one.
Sure. Let me ask you, the time start for the water resources on 11 o'clock or is after that?
It's 11 o'clock.
So I ended exactly on 11 o'clock.
Well, I mean, it takes a few minutes to shut down and get the other one loaded up. So.
Oh, well, here's the thing. So everything will be recorded. So if you have to go to the other, go to the other. You can always come back and watch it again. Okay? Sean, can you hear me?
Yes.
All right. So everything will be recorded. So if you have to cut it short and join the other lectures, go to do that. Because later you can come back and watch our lectures again. Okay? All right? Okay, I don't hear a confirmation. That means you understood, or should I repeat myself again?
No, I heard.
Okay. All right, so let's continue, okay? Our time is precious, all right? So let me open up my screen so you can see my note. There is that. Okay, all right, so let's start, okay? So we talked about shear last time, right? And last time we stopped at the spacing. Okay? So quick review what happened before. So we have VU, which is applied shear, has to be smaller or equal than phi Vn. That is the design of the shear. And this part has two parts, right? Has the concrete part Vc plus the stirrer part Vs, the web reinforcement part Vs. Okay, so now we have to know how much requirement for the steel, right? To do that, we simply use Vs. Okay, it has to be greater or equal than Vu divided by phi minus Vc. Okay, so that is the equation for designing the stirrups. And we know that from last lecture for vertical stirrups, we have one equation. That is Vs has to be equal to AV, where is the reinforcement area of the stirrups, Fyt, yield strength of the stirrups, divided by S, which is spacing of stirrups, multiplied by D, which is the depth of the beam. Okay, for those of you who still have trouble understanding D, basically this is the 45-degree cut on a diagonal crack, and D is this distance right here. Because it is 45 degrees, so we let the side roughly equal to the depth of the beam. Okay, but essentially we're trying to solve is actually requires spacing, right? Solve for requires spacing. Okay, like I said again last time, we have little control of a number of stirrups, a number of the bar that stirrups can have. So essentially, we're just gonna rely on the spacing. So we have to make sure our spacing is smaller or equal than AB, FYT, okay, and multiplied by D divided by VU divided by V minus VC. Okay, so that is the equation to select the spacing for the stirrups. All right, so last time we end up basically here, and then we talked a little bit about maximum spacing requirements. So maximum spacing requirement. Okay, so let me use a different color to show you the diagram. Okay, to show you the diagram. And per our last time's conversation, we say since I will have a section like this. Okay, clean this up a little bit. Okay, and I have a 45-degree cut on the diagonal crack. I have to make sure at least I have one stirrups, okay, which is this one right here, one stirrups along the distance of D here. Okay, why is that? Because we have to make sure at least one stirrups be able to pull the shear resistance along the diagonal crack. Okay, and we say if this is the case, our maximum spacing, switch back to black, maximum spacing has to equal to D over 2, because this distance is D over 2, okay, or 24 inches, okay, 24 inches. But I missed two more equations, actually, two more equations. Basically, the other two equations is AB FYT divided by a 0.75 square root of F prime C, okay, BW. And also another equation, AB FYT divided by 50 BW. Okay, and has to be what? Has to be lesser or the least of all these. Okay, has to be the lowest number of all these. All right, and you can find them. You can find them from ACI code, from ACI 9.7.6.2.2. Okay, and you can find these two equations there, and you can find this equation at the bottom, these two from ACI 9.6.3.3. All right, so the maximum spacing requirement is no matter how wide you want to have spacing between two stirrups, it has to be smaller than all these four equations. Okay, but this is actually not over. This is actually not over. What actually ACI says is, okay, normal condition, this applies. However, though, when Vs, which is the total shear resistance by the stirrups, is bigger than 4 times of square root F prime C BWD, okay? If the stirrups have to provide a shear resistance bigger than that, okay, the spacing is halved. S max is halved, 50%. Okay, what's that? So basically, S max has to be least or lesser of these two. D over 4, no longer 2 anymore. Hey, comparing here was D over 2, but now it's D over 4. Okay, and also 24 right here divided by 2, which is half, become 12 inches. Okay, 12 inches. So this will be the new requirement. This will be the new requirement. If, only if, that the shear resistance provided by the steel is bigger than 4 times square root F prime C BWD. Okay, and now this you can find on ACI 9.7, 0.6, 0.2, 0.2. Okay. All right, so these are the spacing requirements. Okay, so what it says here, right? Apart from the calculation, apart from as required, okay, as spacing has to be smaller than S and max, S max. Okay, so when design, it wouldn't hurt us to do this actually. Spacing would be smaller or equal than as required. Okay, as required, then d over 2, 24 AVFYT divided by 0.7575 square root f prime c BW or AVFYT divided by 50 BW. Okay, and this is one set of condition, and that is another set of equation as required, d over 4 and 12 inches. 12 inches. Okay, so the conditions for these two sets of equation is this. So this is when Vs is smaller or equal than 4 square root f prime c BWD, and this set is when Vs is bigger than that. Okay, so this will help you simplify or streamline your design process. Okay, this will help you streamline your design process. All right, now this is not it. This is not all. Okay, we actually have more conditions that have to satisfy. Okay, so let me name this slide number 1. It's actually a little bit more, but let's just name it 1. And this is 2. Okay, now for the stirrups, okay, for stirrups, there are other limitations. What type of limitations? That we have to make sure FYT is smaller or equal than 60 KSI. Okay, smaller or equal than 60 KSI. Okay, and this is for bars. Reinforced bars, number 3, number 4, you name it. Okay, so people will say, oh, okay, so what if I buy a bar, I purchase the bar that have a strength of 70, for example, 75 KSI. What do I do? In this case, you use 60 KSI instead. Okay? No matter how much strength you can have from the stirrups, you cannot go beyond 60 KSI. Okay? This is just a code requirement. All right? And you can find this requirement on ACI 20.2.2.4. Okay, 20.2.2.4. All right, and this is for bars, but for okay, for WWR. Okay, what is WWR? WWR is welded, for welded. Okay, deformed. Deformed means ribbed. Okay, there was some reinforcement of pattern on the surface of the bar. Deformed wire reinforcement. For deformed wire reinforcement, WWR, okay? Welded deformed wire reinforcement, WWR, okay? And FYT can go a little bit higher. FYT can go a little bit higher, but cannot exceed 80 KSI. Okay, cannot exceed 80 KSI. Okay, so you say, okay, what if exceed that value? Then use it. Capped as 80 KSI. Capped as 80 KSI. Okay, and on top of these, ACI also stated VS, the shear reinforcement provided by steel, okay, maximum cannot exceed 8 times of square root f prime c BWD. So that means if you need a shear reinforcement and your shear reinforcement provides shear resistance, that resistance cannot exceed 8 times square root f prime c BWD. And this you can find ACI 22, 0.5, 0.1, 0.2. Okay, 22, 0.5, 0.1, 0.2. All right, so here I want to stop a little bit, talk about this. Okay, so you can see this slide number 2. You can see I have so many restrictions on designing shear, right? First of all, I'm talking about the shear spacing required. Then it has to be at least 1 bar along the spacing D, and which means spacing has to be lesser than D over 2, 24 inches, and blah, blah, these 2 equations, so 4 equations. And I had to compare my shear resistance from reinforcement to see if it's bigger than 4 times this much. If it's bigger than that, I have to halve my spacing. And even more, and I have a stirrups constraint that my strength of stirrups cannot go over the 60 KSI if it's bars, and cannot go over 80 KSI if it's welded deformed wire reinforcement. Okay, on top of that, my total reinforcement provided shear cannot exceed 8 times square root F prime C BWD, right? So what does it say? Basically, it says, okay, I want to put some note here. Okay, I want to put some note here, note. Okay, note, there are several constraints on shear. There were several constraints on shear. So if check, first of all, step, you need to check if Vs is smaller than A times square root of BWD, square root of F prime C BWD. You need to check that first, okay? If not, increase your concrete section. Increase B, W, or D. Means change section, okay? Okay, so the meaning of that basically tells you if you need so much steel to resist that shear force, that means your section is not big enough. Okay, just forget about it and change a bigger concrete section. Okay, so that's step number 1. And then check if Vs is smaller than 4 times square root F prime C BWD. Okay, if so, use spacing of S required from the equation. Okay, and then the D over 2, then 24, the AVFYT divided by 0.75 square root F prime C BW, and AVFYT divided by 50 BW, use this equation. If not, okay, your spacing will be least of required, of course, D over 4 and 12 inches. Okay, 12 inches. All right, so this basically laid out your design process for shear, okay? And this is actually for spacing, right? Spacing requirement. That's all there is. Okay, so now let's talk about the other thing. Okay? What's the other thing? We need to talk about location of shear. So this is called location of critical section. Okay. Now the problem or the interesting notion behind it is shear actually has to be designed for different shear forces along the beam, right? And the shear diagram, for instance, I want to take some example. If I have a simply supported beam at uniform distributed loading, the shear diagram, so this is structure, and this is shear diagram. For the shear diagram of this, I have this shear and this shear. Now the sign can be a little bit flipped, depends on which system you're talking about, but that's the shear diagram, right? And then if I have a simply supported beam and I have a shear like this, oh, sorry, this is not right. Okay. I have a shear diagram maximum here and the middle 0. And then this is that, right? So now, as you can see, for different structures, I have different shear diagram, okay? So I need to know where is the critical section to design my shear. So for the top structure, of course, the critical section is right here, right? We're near the end, so critical section, critical section right here near the end, okay? And for simply support beam with concentrated force, my critical section is here, here, here as well. You see, so when you design shear, you have to pick the critical section first. Critical section first. Okay. Now, someone may say, okay, do I need to draw the whole shear diagram to know where the maximum shear is to design a member like that? No, you don't have to. You don't have to, because the code has mapped out for you already. The code has mapped out for you already. Okay. So let's take a look. Let's take a look. Okay. So ACI says this is a list of critical sections for different structures, and you can find this from ACI 9.4.3.2. Okay, you can find it here. You can find it here. All right, so here we go. Okay, we know now if I have a beam end sit on top of support. Okay, this is a rubber neoprene support on the column, like so, and this is just the cut. Okay, and I know my critical, well, actually have to draw out the distributed load. Okay, and this under distributed load, uniformly distributed load. Okay, my critical section is right here. So I draw 45 degree, and it has to be originated from the support. Okay, originated from support. So the distance d away okay, this somehow don't like this very much. Sorry, okay, let me get this in a better drawing. 45 degree. Okay, so this right here is the critical section. Okay, this is the critical section. Okay, so let me use double line, a little bit heavier so you can see it. So it's distance d away from a line of support. Okay, this is line at support. Okay, distance d away from line of support, Okay, so this is scenario number one. So I'm just gonna put some cases. Okay, so if this is case A, okay, case B, I'll have a different structures, right? I have a beam column joint. So this is the beam column joint. Okay, and also it has uniformly distributed load on the shoulder of the beam. Okay, and then the critical section would be actually distance d away first. You notice I'm drawing the diagonal crack first. Okay, so distance d away from the intersection line here. Okay, so this is d and this is 45 degree. Now this, both are the critical sections. Okay, critical sections. Now this is case 2 or B, and C, what if I have end bay at the beam column joint, end bay? Okay, end bay looks like just like this. Okay. Now, if I have N bay, I also have distributed load here at the shoulder. All right, and my critical section is gonna be where? Gonna be same thing, gonna be 45. So these are the critical sections. Sorry. So now like this writing thing. Okay, so all this. Okay, all these are critical sections. Okay, now it's interesting because if I draw the shear diagram, okay, and this is a line of support. Cut. Okay, if I draw the shear diagram, right, I'm gonna use N bay. Be careful, okay, how I draw it. This is N bay. I'm gonna use this N bay. This is a line here extension, line here extension. Okay, and I'm gonna draw the shear diagram. Now, surely it looks like this. So it has the maximum shear right here, and maximum shear right here, maximum shear here. Notice these are same level, and maximum shear right here. Again, this is same level. So the shear diagram is gonna look like this. Okay. Okay. But when I design it, I'm not going to use the peak value because I'm just going to use the critical value right here. Critical value right here. Okay, so I'm going to use this shaded area as my actual design shear. Okay, so be careful, there's a slight difference. Okay, so these are three cases we see normally, most often. Okay, most often. However, there are other cases as well, okay? So other cases. Okay, you can find this, from ACI. R revision, this is revision R 9.4.3.2. So where there are some exceptions, okay? So if I have a beam sitting on the column, but the load is actually nearby the support. Okay, so where I actually have a load at the lower end of it. So you can see it, this is a little bit strange, right? This is a little bit strange, but actually if I see from the side view, this is what you're seeing here. Okay. Okay, so kind of like a Kobo, okay? So when I have this case, okay, previously, okay, we call previously, you see from A, this is the critical section, right? Distance D away from the support line of support, okay? That was the critical section. Now with this case, I have to add one right here. That means if I want to design shear for this section, I need to use this section's shear force as well, okay? So this is the critical as well. So on top of the previously D, you have two critical sections now. You have two critical sections. You need to check both. Okay, this is for one exception. Okay, another exception. If I have a column, actually a hanger column, somewhere like a balcony, and have a beam going this way. Okay, and this is the beam. And now if I have distributed load going this way, okay, and I need to check the critical section right here. Okay, I need to check the critical section right here. Okay, so this is called the case where beam is supported, by tensile force. Okay, this is a beam, and it's supported on this, and this is a tensile force. Okay, so that's another exception. And also have exceptions like this. So other cases continue. If I have a beam and have a concentrated force, okay? So if I have a concentrated force, then right at the concentrated force, I need to consider for shear design. Okay, I need to consider for shear design. And another case, I have also a 3D view if I have a girder. Okay, so let me try to draw it right. If I have a girder, okay, horrible drawing, I realize, but I'm doing my best here. Sorry for that. And this is the girder beam joint. Okay, so this is the girder. Okay, and this is the beam. Okay, and then I need to consider a critical section like here. So the critical section is right here at the joint. Okay, at the joint. So critical section. Okay, so these are the critical sections, right? A, B, C, other cases. These are the critical sections you need to consider for shear. Okay, all right. So now we also add something. So this is concentrated force. And this is a girder, beam girder intersection. Okay, this is edge loading. Okay, this is beam supported by tensile forces. Okay, so let me label this as other case 1, other case 2, other case 3, other case 4. Okay, so all these cases you need to understand. Okay, you need to understand, and we will have them in the exam. Okay, we'll have them in the exam. All right, so at this point, we're basically ready for design. Okay, ready for design. Let's see where are we at. So this slide 5, slide 6. Okay, ready for design. So I'm going to show you an example. Okay, so design for shear. And today is going to be a simple case. Okay, simple case. All right, how simple? This simple. I have a rectangular beam. Okay, I have the bottom 4 number 8 bars. I have a width of 12 inch. I have a height of D plus cover, right? So the D equal to 21.5 inch, and the cover is actually 2.5 inch. So H equal to what? Okay, 24 inches height. Okay, so this is the beam. This is beam. And this example is for the beam below or for the beam on the left, okay, check if the section is adequate. Is adequate to resist shear. VU. Okay. If not, design as required spacing. So actually, let me be more general. Design web reinforcement. Okay, so this is the question, and I'm going to give you some detailed information. So F prime C concrete has a 4 KSI strengths. Okay, and yield strength of the stirrups is limited to 60 KSI. This saves you a lot of hustle, and it's a normal weight concrete. Okay, and simply supported beam. Okay, and now I'm going to give you a list of VU. Okay, so A, 12 kips. So VU equal to KSA 12 kips. B, 24 kips. C, 54 kips. D, 77 kips. And E, 128 kips. Okay, so you're going to check if the shear hold for all these applied shear forces, Okay, so now let's take a look. So A first, VU equal to 12 kips. So first thing first, I need to make sure VN is greater than VU. And from the concrete we know that equation used most often 2 lambda square root F prime C BWD.
Could you scroll up for just a second so I can write down all of the cases?
You mean this?
Yes.
This.
Or, no. Just what you just wrote.
You mean here?
Yes, those 5. Yes.
Okay, 12, 24, 54, 77, 128. Okay. Okay. So I'm going to do this. I'm going to scale it a little bit. Okay, so you can see it simultaneously. All right. So now, if I do that, and then I'm going to bring the number in 2 and times lambda. In this case, it's normal way. So lambda is 1.0. Okay, 1.0. And then BW, where is my width? 12 inches. Okay. And then I have a depth of 21.5 inch. Okay. 21.5 inch. Okay. Sean, I'm going to mute you. Okay. So if you want to speak, you can unmute again. All right.
Oh, sorry.
No worries. Okay. Thanks. Appreciate it. So now I can bring the number and calculate it, and VC concrete gives me 32634 pounds inch. Sorry, pounds, no inch. Okay. And that is 332.6 kips. Okay, and now that is the shear resistance provided by the concrete. So PVC strength reduction factor for shear 0.75 flat number and multiplied by 32.6 kips, and that gives me a 24.5 kips. Okay, and this number is indeed greater than VU. Okay.
Dr. Wu, I
Yes.
think the F prime C, you forgot to put the 4K.
Oh yeah, sorry about that. You're right. Thank you very much for reminding me. Okay, so F prime C here is 4,000 psi. Okay. Thank you very much for reminding me that. Okay, appreciate it. Yeah, 4,000 psi. Okay, 4,000 psi, and use psi in the square root. Okay, use psi under the square root. Okay. All right, good. So VVC is the stress reduction factor added resistance from concrete's 24.5 kips, which is bigger than the 12 kips of applied shear. But this does not mean we don't need stirrups. Okay, well, we don't need the stirrups. Why? Because we have to say that if VVC divided by 2 is 24.5 kips divided by 2 equal to a 12.25 kips. If that is greater than VU, which is the case, okay, half of the shear resistance provided concrete alone is bigger than the applied shear. In this case, we can say, okay, no stirrups needed. Why? Because remember, if, we're going to use red here, okay, if VVC divided by 2 is not, so it's smaller than VU, but VVC itself is bigger than VU. In this case, need minimum shear reinforcement. Okay, need a minimum shear reinforcement. Okay, and actually we have a number for that, right? We have a number for that, but since we don't need it in this case, we're just gonna omit it. Okay, just gonna omit it. Okay, so this is case A. All right, so now let's jump to case 2. Okay, so VU equal to 24 kips. Okay, VU 24 kips. Then for VVC, follow the previous case, VVC is 24.5 kips, which is bigger than VU. Okay, bigger than VU. Right? However, though, we have the case that VVC divided by 2 smaller than VU, right? From previous case, smaller. So minimum stirrups required. Okay, so what is the minimum amount of reinforcement required? We don't actually do that. We just check our max spacing. So S max, okay, has to be the smallest or least of these following. What are the following? D over 2, okay, 21.5. That is depth divided by 2 equal to 10.7 inch, 10.75 inch, 24 inches. AV FYT divided by 0.75 squared F prime C BW. And that is Brennan number 2.11 inch squared. Y2, okay? Y2. I want to emphasize this, okay? And don't you forget, all of us, the stirrups is in a U shape like this. It has 2 cross sections. So for number 3, bar, each has 0.11 inch squared. So I have each have 0.11 inch squared. Okay, sorry about this. Let me just 0.11 inch squared. And I have 2 legs. 2 legs, okay? So 2 multiplied by 0.11, okay? I will emphasize this every time we write it, okay? So you should not make any more mistakes on this, okay? These are 2 legs, number 3 bars, okay? Now people ask, why you select number 3 bars? So let me just say this, okay? Always try number 3 or number 4 for stirrups. Okay, because these are the typical number we use. All right, typical number we use. Okay, coming back. So FYT is 60 KSI, so 60,000 PSI for the yield strength of the bar. Okay, and divided by bottom here 0.75. You notice in terms of shear, everything's in terms of PSI. Square root of 4,000, and BW is 12 inch. Okay, and I have this number down to be a 23.2 inches. All right, and don't forget our last but not least equation, AVFYT divided by 50 BW. So this is 2 multiplied by 0.11, and then 60,000 divided by 50 multiplied by 12 inches, and I have this one to be 22 inches. Okay, now the equation or the required spacing for maximum spacing demands for the smallest number, so this number governs. The 10.75 governs, okay? Govern, okay? So S max, let me just use this sign here, okay? So therefore, S max equal to a 10.75. All right, and then I want to design for shear, right? So this is S max, so I just need to have a spacing smaller than S max. Okay, and keep in mind, this is for number 3, stirrups. 2 legs, U-shaped stirrups. Okay, so I'm gonna say use number 3, U-shaped stirrups at 10-inch spacing. Okay, so basically what I'm saying is S equal to 10 inches smaller than S max equal to 10 3/4. Okay. All right, so this is the second case. All right, for B, that is 24 kips. For B equal to 24 kips. You see? So now let's go to the next one. As shear, applied shear increases. Let's see here. Again, I'm going to stop using page number because they are all continuous. Okay. So for case C, VU is 54 kips. Okay. So here's my.
Oh, Dr. Bob,
Yeah.
wouldn't you just, why would you not just pick the largest VU and just design the entire beam accordingly?
Well, here's the problem, right? We need to solve for all of them, right?
So could you just solve for the largest one to make the beam consistent?
No, I cannot. This is not a consistent game, right? Look, in the case A, right, we have a low shear. So in this case, I don't need to provide any stirrups at all. In case B, I have a medium shear, so I need to provide some stirrups, okay? As you go along, you increase the shear force, you see different spacing requirement. And matter of fact, in the beam, the shear force distribution is not uniform, right? So you can actually change your spacing in the beam. We'll talk about that next lectures. Clear?
If you're constantly changing the section of the beam, I would think that would make it a lot less economical to build.
Yes or no? It depends on how much of stirrups cost, right? Right? So I think you're jumping into the applied problem right now, but today let's come back and solve this problem first, okay? Okay. All right. Yeah, well, Byron is right, okay? They're just different beam scenarios. Yes, indeed. For now, it's just theoretical, okay? It's not one beam, okay? Sean, you understand? Sean?
Oh, yes, okay, yeah, that's fine.
Got it? Okay, good. Let's go on, okay? I mean, I agree with you. If it's just one beam, we have to think about different scenarios. But here, it's just one beam with different loading cases, okay? It's not one beam. All right, you can think about it as multiple beams, okay? Okay, all right. Okay, so let's continue, right? So V equal to 54 kips. Sorry, I need to rush a little bit. I want to finish this. So since VU is 54, I'm using red, this is my thought process, okay? It's bigger than VVC. For sure, VVC is 24.5 kips. Means concrete itself is not enough, so we need stirrups for sure. I need it. Okay, we need stirrup for sure. So now, coming back, VVN will have 2 components now, concrete and steel. Okay, and has to be bigger than VU applied. All right, so the required shear from stirrups should equal to VU divided by phi minus VC, and that is 54K divided by 0.75, okay? And I know some of us have a problem with my 4, so I'm gonna write it better. 54 divided by 0.75 and minus 32.6 kips, okay? And this gives me the required shear from the steel has to be equal to a 39.3 kips. Okay, but before we go any further, this is required steel shear, right? Required shear from steel. We have to make sure this is smaller than 8 square root of prime CBD or not, okay? And turn out this number is 130.6 kips. Okay, so satisfied. And also we have to check if VS required is bigger than 4 times square root of F prime CBWD, which actually is 65.3 kips. Okay, turns out it is not. So it is smaller, right? Because this is 39.3 kips. Just calculated. Okay, so now if all these are checked, now the spacing basically S max will equal to what? Equal to all these things we just write, all these things we just wrote. Okay, so I'm just going to copy this. Okay, all the things we just wrote. Ah, sorry. Let me see if I can, well, let me try to do this. All this requirement which is finished, and I'm going to oops, okay, you know what, let me just forget about it. Maybe let me do this. Okay, do this. Okay, let me try to, I'm learning this slowly, okay, so here is my stuff. I'm just going to circle it out and bring it over here. Okay. Okay. I'm going to copy and I'm going to paste. So I still have it here too. Okay. All right. So I'm lazy. I'm sorry. Okay. So here now. Okay. So I'm trying to say is after all this, check this maximum spacing calculated before still hold. Okay. So now the max S max. Let me rewrite it better. So the S max is still 10.75 inch. Okay, still 10.75 inch. All right. So if that's the S max, the required spacing though, as required, okay, is what? As required is AV FYT multiplied by D divided by phi. Sorry, it's actually VS required. Okay, so you can write the other way, VU divided by phi minus VC, which is VS required. Okay, and I bring number 2 legs, 11 inch squared, 0.11 inch squared of area, 60,000 psi for the steel, and depth is 21.5 inch, and divided by required, which is 39.3 thousand pound. So I get a spacing equal to a 7.26 inch. Now this spacing, required spacing, is smaller than the maximum spacing. So I go with this one. And now you notice that I'm using number 3 as well. Okay, I use number 3 as well. So now I'm going to say use number 3 at a spacing, if the required spacing 7.26 inches, okay? I'm going to use smaller spacing, which is 6 inch. Okay, so this is the less spacing required. Okay, all right.
Is there
I'm
any
just
reason
gonna.
that we couldn't use 7 inches?
Oh, we can surely we can use 7 inches. I'm gonna use 6 inch because I like the number as half foot.
Okay.
Right? Yeah, you're right. You can use 7. Some people like 7 is better actually. Okay, a lot of 6 is tighter. Okay, so I have to stop here today, but let me recall quickly. Okay, and so if you, those of you who have to leave, you can leave. But let me quickly recall. Okay, I want to show you several things. So now, as you can see, as my applied shear bump up, so I'm looking at a case, no stirrups required. Okay, and minimum stirrups required. Or you can just think about maximum spacing. Okay, and this is actually required spacing. Okay, so today we see that for a same beam, for a beam have a different load. Okay, for a beam applying different load, I can design differently just based on the shear forces. Some cases I don't need stirrups at all. Some cases I need a minimum number of stirrups. Some cases I need a lot of stirrups. Okay, and you'll see later from case D and E, we have even better or other variations of spacing. And just as Sean mentioned, if I have a beam, okay, just some food for thoughts, okay, if I have a beam and I have a distributed load, and the shear diagram, as I know, look like this, triangles, right? So can I design the stirrups correspondingly, right? To have almost no stirrups in the middle, little bit stirrups in this zone, and tighter stirrups as I go to the end of it. Okay, and why do I need to do that? I want to save the cost. Okay, all right, I guess this is where we end. So I'm going to end my section here, and I'm going to post the recorded video soon. Okay, thank you very much, and talk to you on Thursday. Okay, talk to you on Thursday. Thanks. Bye now.